So
here's the thing. I don't know how to make my pointer show up when I play. Do you know how to do this?
we see your cursor.
No, I know, but like once I play the slideshow,
No.
Can you see the cursor?
Yeah.
You can? Oh, okay, good. Good.
Yeah. Okay. So let's start. So I'm really happy to welcome my buddy Lukasz to give a seminar. Lukasz, did his PhD in Stanford in string theory. Is that right?
Yeah.
And then he was a postdoc in several distinguished places like Caltech, Station Q, Berkeley. He also got this New Horizons Prize, right?
Yeah.
Oh, yeah.
Very exciting.
So yeah, and now he's in the University of Washington. He's going to tell us about how quantum memories forget. I can tell you how classical memories forget because I kind of experience that all the time. But
yeah. Oh, cool. Thanks so much for the invitation, Nate. It's great to be here virtually. I feel like I'm jet lagged, even though I'm not actually there, so that's good. Let me actually do this. So I'm going to start like this, just because there's something I want to look at on my screen. But a couple slides in, I'll go into full screen mode. So as long as you can see this for now, it'll just be like this, just for the first couple of slides. Okay. So right. So this is some work that I've done with Jungwon Ha and Matt Hastings, who are actually both at Microsoft Research right here in Redmond. So I'm at the University of Washington in Seattle, and they're just across Lake Washington. It's like 15 minutes away. So I collaborate with them quite often. So this is so let me start off with just the plan of the talk. So this is actually sort of an edited version of a previous more technical seminar, where basically what I did was I added a few slides to the introduction. So let me just briefly describe sort of the class of systems that we'll be looking at. So in this whole talk, all the actions going to be happening in a Hilbert space of a spin chain. So really we'll just be considering n spin 1/2, or in other words, n qubits, if you like to think about it that way, arranged on a line. And the dynamics is going to be governed by unitary operators, which you can think of as quantum gates, as well as measurements. Okay, so this is not sort of your usual Hamiltonian system where you have a many-body quantum system governed by a Hamiltonian, but rather there's going rather here we're going to have sort of two components. We're going to have unitary gates, or the usual unitary gates, but also measurements. So in particular, this is an inherently probabilistic, inherently stochastic system, because measurement outcomes are inherently stochastic. So in other words, we're not going to be following the evolution of a single quantum state, but even if you do start with a single quantum state, we're ultimately going to end up with an ensemble of quantum states. Okay, so this is a stochastic system where you track an ensemble of quantum states. And so in this context, recently people found something interesting. They found a sort of new dynamical phase transition, which separates two phases with different behaviors of entanglement entropy. So this is, because this might not be familiar, this is something that I'll review for the first part of the talk. There's also a related phase transition, which involves starting not with a single pure state, but rather with a maximally mixed state, and seeing whether that maximally mixed state gets purified or not at late times. So here, somehow there's a competition between measurements, which tend to purify a state, and unitary operators, which kind of tend to scramble it and prevent that kind of purification. So I will review all this in the first part of the talk. So the first part of the talk is just review. The new results that Matt and Jungwon and I came up with are going to be in parts 2 and 3. So, I'll at least be able to state them. I might not explain them fully. But these new results involve, so the first one, part 2, involves looking deep inside this so-called mixed phase. So this is the phase of the quantum system, which is governed mostly by unitary evolution, but every once in a while there's a measurement that's sort of sprinkled in. Okay, so this is sort of deep in the mixed phase where it's mostly unitary evolution with sort of rare measurements. So, you know, so according to this picture of these phase transitions, I'll review a maximally mixed state in this mixed phase does not purify. So in other words, there's some threshold measurement rate that needs to be reached before the state that will actually purify. So, and this is something that's seen in numerics. So what we did was we actually studied the very long time behavior deep inside this mixed phase, and we found that actually, indeed, the state does purify ultimately. It just happens on a time scale which is exponential in system size. So to do this, we actually introduced a pretty simple sort of zero-dimensional model that's we think sort of an appropriate caricature of this limit, which we were actually surprised that hadn't seemed to be studied before. So this is one.
You say that any rate of measurement is sufficient to purify, you know.
Ultimately, in a very long time, yeah. So that's right. So what this purification phase transition is it's really a phase transition between states that purify on a polynomial timescale and system size, and ones that purify on an exponentially long timescale. Yeah. Okay. So that's one of the results. The other result that, you know, hopefully I'll have some time to talk about involves free fermions. So, okay, so why look at free fermions? So, you know, one of the sort of challenges with this whole field is actually getting results here. So most of the results, you know, come from numerics. There's not a lot of exact results, and, you know, simulating a many-body Hilbert space is hard. Simulating sort of general many-body evolution is difficult. So it's nice to have, you know, some simpler class of dynamics to look at in order to simulate, you know, these various phenomena. So indeed, in the context of, you know, this original work on entanglement and purification transitions, people don't actually sort of look at the most general possible unitary evolution, but rather they look at so-called Clifford evolution and Pauli measurements. So this is a subset of unitary operations which are basically easy to simulate on a classical computer. Okay, they have sort of enough structure that they're easy to simulate on a classical computer, and so they're simple enough to easily simulate, but they're sufficiently complicated to actually show this you know, show this entanglement and purification transition at a threshold, finite threshold measurement rate. So that's you know, that's what makes them nice. So you can ask the same thing about other classes of easy to simulate dynamics, such as free fermions. So, you know, with free fermions, you can define free fermion evolution. You can define sort of free fermion measurements. You know, just measure fermion occupation modes, measure fermion bilinears, and you can ask the same question. You know, can you see these transitions in free fermions? And, you know, one thing that might lead you to be optimistic is that, you know, if with no measurements, just unitary evolution, you can indeed realize sort of the volume law float for entanglement, and certainly with, you know, all measurements, you'll have an area law, so you sort of have the two endpoints. But what we showed is actually in the context of free fermion models, as soon as you add in any measurements, so you know, with arbitrarily small measurement rate, the system purifies fast. So it purifies in polynomial time and system size. So the measurements just kind of kill this volume law phase immediately in the context of free fermions, which is not something that happens in the more general context. But so unfortunately, these free fermion models can't really be used to study these phase transitions. Okay, so that's the introduction. Any questions before I sort of launch into the review of entanglement and purification transitions? Okay, yeah, and feel free to stop me with questions anytime. So, right. So here's my review of entanglement. Let me start with entanglement transitions, because this is the thing that people realized first. So I stole this figure from a paper by Matthew Fisher. This was one of the original papers on entanglement transitions. So let me just briefly describe the setup here. So first of all, The Hilbert space here is denoted down here at the bottom. So this, this figure describes a Hilbert space of little n qubits. So, it's just the usual many-body Hilbert space that involves a tensor product of two-dimensional local Hilbert spaces. In our study, we're always going to start with a certain initial state, which you can just assume to be the trivial product state, let's say in some specific basis, maybe spins up in the sigma z basis or something like that. So that's the Hilbert space, that's the initial state, and then we're going to see how that state evolves. So as I mentioned, there's two kinds of evolution operators. So all the evolution operators are, in the language of quantum information processing, they're just gates that act on a pair of qubits, and they act in this fashion that's represented in this figure. So here time flows from the bottom up. And the two kinds of gates are, first of all, you have 2-qubit unitary gates. Okay, so these are just gates that act on a pair of qubits at a time, and you would like to choose these to be Haar random. So in other words, just take a completely random unitary acting on this 4-dimensional Hilbert space of 2 qubits. But as I mentioned before, in order to numerically simulate this, you don't actually look at Haar random 2-qubit gates. You look at Clifford random 2-qubit gates. So Clifford random or Clifford gates are ones which map Pauli operators to Pauli operators. So I think they actually in this paper did numerical simulation with both Haar random and Clifford random gates. But obviously with Clifford random gates, they can go to much larger system sizes. So that's one kind of gate. The other kind of gate involves measurements. And really what you'd like to do is just single site measurements here. But for some reason, I think just for technical convenience, they found it easier to just pick a subset of these 2-qubit gates and do measurements on them. So in other words, what they do is, for some subset of these 2-qubit gates, which I've denoted in blue, they apply a projective measurement on, I think, sort of arbitrarily chosen. They arbitrarily chose the first qubit to measure projectively, and then they apply another unitary evolution. But there's actually many different sort of microscopic models which show the same universal behavior. So the way I'm going to discuss this, I'm going to actually ignore this U that's done here. So it doesn't really matter. It's it's in the same universality class. But the important point here is that this is really a measurement. So this is not a forced measurement. This is really a measurement. So in other words, P is a projector, but you apply either P or 1 minus P with the probability that's sort of the usual probability associated with a quantum measurement. Okay. So
in this sense, Lukasz, wait, I'm confused. So you keep both options, or you post-select?
You keep both options. So even if you start with a pure state, because you keep both options, you're going to end up generically with an ensemble of pure states.
So the way I have to think about it, I do the measurement and then I trash the result, and I forget about it.
What do you mean by trash the result?
I mean, I forget what the result was, and I keep both of them.
Yeah, that's right. Yeah. So I mean, for example, if you start with an eigenstate of sigma x and you measure sigma z, then you get an ensemble with probability 1/2 you get a spin up, and probability 1/2 you get a spin down, and so you keep track of this ensemble.
I end up with a mixed state in that case. I don't end up with a pure state because
yeah, so that's right. But I don't want you to sort of just think about keeping track of the density matrix. I want you to actually keep track of the whole ensemble. Mm. So the stuff that and I can give you a specific example why sort of the density matrix is not enough to yeah, maybe ask that later. But I really want you to keep track of this entire ensemble. Sorry, go ahead.
I thought it's the same. Keeping the ensemble is a density matrix.
You can have multiple different ensembles give you the same density matrix. So any orthonormal basis of a Hilbert space, if I take an equal mixture of those states, that gives me the maximally mixed state, which is just the identity.
Right.
But if those, we really care about the character of those states in the orthonormal basis. So like if I take an orthonormal basis of product states, those sort of have zero entanglement. But if I take an orthonormal basis of very entangled states, those might have non-trivial entanglement. And ultimately, I'll want to average the entanglement over this ensemble.
Mm-hmm.
So I want to keep track of this ensemble.
Yeah. Mm-hmm.
Okay. Okay. Yeah, and feel free to interrupt later if there's something that's still confusing. But so like I said, this is a stochastic process. There's lots of randomness here. There's randomness in actually several different places. So you make a random choice of unitary. You make a random choice of sort of at each gate whether to apply a unitary gate or a measurement. So this introduces a tuning parameter little p, which is the probability with which you actually make a measurement, and so that's random. And then there's sort of the inherent randomness of these projective measurements. So it turns out that this is the important randomness. So these other sources of randomness you can actually get rid of. So you can make models that realize these kinds of entanglement phase transitions where these unitaries are not actually random. It's actually a Floquet system, and you don't even have to sort of randomly choose whether you do a measurement or a unitary. In other words, you can sort of do your measurements in various fixed positions scattered throughout the system. So really, so you can get rid of the randomness here. And I know Matthew and company have sort of looked at these Floquet models with sort of fixed locations of measurements, but this randomness you cannot get rid of. So okay. So let me just review sort of the limiting cases here in terms of.
Are you projecting on a random basis, or you're projecting on the same basis, a fixed basis?
Same fixed basis. Sigma Z.
Okay.
Single site Sigma Z projectors. Yeah. Yeah. So here are the limiting cases. So the quantity that you want to look at is so you have this large spin chain, and you want to look at some subset of L sites. I really have to take this to be on the left side of the system. It could be, and I didn't mean to imply that these are open boundary conditions either, but that really you just take some contiguous set of L sites, maybe with periodic boundary conditions, maybe not. And what you want to do is for a given quantum state, you can construct a reduced density matrix on this set of L sites, and you can compute its entanglement entropy. So just minus trace of rho log rho. Okay. And so then what you want to do is you want to the thing that we want to look at, the sort of order parameter for this transition, is looking at the ensemble average of this entanglement entropy. So in other words, take this quantity. So for each pure state in your ensemble, you construct this reduced density matrix real well. You can compute its entanglement entropy, and then you take that quantity and average it over all states in your ensemble with the probabilities with which they appear in the ensemble. Okay. So this is, again, sort of relates back to what I was saying earlier. It's important to keep track of actually which states you have in your ensemble. If you have, all simple product states in your ensemble, this ensemble average will just give you 0. If you have complicated entangled states in your ensemble, which again might lead to the same overall reduced density matrix, or the same overall density matrix, then this ensemble average will be non-zero. So you have to keep track of the actual states in the ensemble. So really you want to be thinking about sort of individual quantum trajectories. That's really the way to think about it. Think about sort of what a typical quantum trajectory does. Okay, so the endpoints of this is if you do all unitaries and no measurements. So if you just apply unitary gates, it's sort of well understood that this, even if you start with a product state, okay, there's no random. You don't really have to think about randomness. The entropy will go to this block entanglement entropy will go to a volume law. So the state just becomes very entangled. I mean, you already know this in the context of Floquet systems. Here, it's even sort of more random because there's just completely random unitaries. So people understand this very well. Obviously, if it's all measurements and no unitaries, you're just measuring all the time and not evolving, you start with the product state, you stay in that product state, and nothing happens. So the entanglement is just always 0. So that's in particular area law. So now what numerics shows, and people have, I mean, this is just the original paper, but people have since confirmed this, is that you can investigate what happens at intermediate measurement rates. And so what people see is that there seems to be a critical threshold value of this measurement rate P, at which you go from volume law scaling to area law scaling. So this is sort of 2 different graphs that represent the same data. So here, the different curves represent different system sizes. And on the horizontal axis, you have the measurement rate P. So on the left is a small measurement rate, and this is the volume law, where you can see that, okay, so here they didn't look at, so here I think, the entire system had length L, and they looked at some L/4 sub-interval of the entire system. So it's slightly different notation than what I talked about. But in any case, you can see that there's a volume law for the ultimate entanglement entropy at which a state saturates at small measurement rate, and for large measurement rate, it depends on system size. So it saturates to some kind of a quantity that's independent of interval size. So this is the area law. Here you represent the same information, except the different curves here correspond to different measurement rates, and it's just graphed as a function of system size L, so interval subsize L. And so here you can see that entropy saturates to an area law for large measurement rates, and then past a certain threshold, you go to volume law. So all these are, yeah, sorry, go ahead.
And the initial state it's just a random state in Hilbert space, or is it the
initial state is a product state? Is just the sigma z product states, all spins up.
Okay.
But then you have lots of randomness in the way you choose your unitaries and whatever. So it rapidly evolves in some complicated way. Mm-hmm. And so all this is, they go to system size of like 512 sites. So this is all done with Clifford unitaries. So the way that this is actually, the way that you don't obviously track something in a Hilbert space of many-body Hilbert space of 512 sites. What you really do is you leverage the fact that these Clifford unitaries preserve Pauli operators. So what you really do is leverage the fact that these are all stabilizer states during the evolution. So a stabilizer state is just one that's an eigenvalue plus one eigenstate of some complete set of Pauli operators. So the starting state is a sigma z equal to plus one eigenstate of individual sigma z's on the individual sites. And then the Clifford unitaries have the property that they take each of these sigma z stabilizers to other Pauli strings, not linear superpositions of Pauli strings, but Pauli strings. So what you can actually do, what these people do to do in numerics, is they actually follow the way that these stabilizers evolve over time. And that's something that's easy to keep track of. And then the entanglement can be just computed from knowing what the stabilizers are. Okay.
So again, this transition is between which 2 states? I mean, can you again, what is the meaning of this result of this transition again?
Yeah, so the transition is as a function of measurement rate, and it's a transition in the way that the state behaves at asymptotically late times. So at small measurement rate, as you evolve in time, the state gets more and more and more entangled. So the way you measure this is you can look at any imagine that you're in the thermodynamic limit of infinite system size. You can imagine looking at any subinterval of length L, and what you'll see is that in time, as you're tracking your state in time, ultimately the entanglement entropy, the block entanglement entropy of a subregion of length L becomes of order L. It's some constant times L. So in other words, these states at late times exhibit volume law entanglement entropy for any subregion at small measurement rate. At large measurement rate, this is not the case. At large measurement rate, the entanglement entropy saturates to a constant. And so if you take larger and larger subregions, it just stays approximately constant.
So that's kind of
Rate is-
a many-body version of the Zeno effect. I should think about it.
Yeah, exactly. And in fact, I think that was the subtitle that these people had: many-body version of the Zeno effect.
Okay.
Yeah, exactly. So if you measure it enough, it somehow can't become too entangled. Was there another question there?
Yeah, so the rate is a comparison between the rate of the unitaries and the rates of projections.
Correct.
Thank you.
Exactly. Yeah. Mm-hmm. Yeah. Okay. So let me actually sort of give one naive and actually incorrect argument as to which actually shows why this result might be surprising. So this was actually published in a paper, some version of this argument with sort of appropriate caveats. So that, yeah, this is a naive argument which shows you how surprising this result is. The fact that there exists a volume law phase with a finite measurement rate. So here's an argument which will try to show you that any finite measurement rate actually kills the volume law phase. So it's an incorrect argument, but bear with me for now. So let me imagine some large sub-interval L inside my system, and let me just sort of imagine a single time step or a single layer in this quantum evolution. So sort of two things happen during this layer. So in red, I've denoted the effect of unitary gates. So unitary gates act everywhere, but if I just care about how the block entanglement entropy of this subinterval evolves, the only unitaries which increase that entanglement entropy are ones which act near the boundary of my system, so near one of the two endpoints, right? Because they have to entangle something within this interval L with something outside of it. A unitary that acts deep inside this interval doesn't change the entanglement between this interval and the outside. It's, you still have the same Schmidt coefficients, just a slightly different Schmidt decomposition. Same with unitaries that act far, far outside of this interval. So that's the case for unitaries. Now, as far as these measurements, so these measurements act to decrease the entanglement entropy. If you make a measurement, then on a given qubit, let's say on a given spin and a half, then that the value of that spin becomes known, and the state is just some tensor product state of that qubit being in whatever spin up or spin down with the rest. So that intuitively that decreases entropy, and so there's a competition, you might think, between these two effects. And because the unitaries only increase entropy near the boundary, whereas the measurements decrease entropy sort of everywhere inside this interval, the measurements sort of win. Okay, so the entropy density, the way that it would evolve under this time step is there would be an increase, which goes like C over L, because entropy itself would only increase by a constant due to the unitaries, but there would be a decrease due to the measurements, and the decrease would be like 1 minus P. You might think, because you might think that every time you do a single site measurement, you sort of learn 1 qubit's worth of information, so your entropy goes down by log 2. And so if you believe this, then you see that as L goes to infinity, the only way for this to be true is if the entropy density goes to 0. Okay, so there's no way that this can sustain a volume law for entanglement entropy. So any finite measurement rate would have to kill the volume law. This is the sort of naive argument. However, there's a problem with this argument, and the problem is that is basically this assumption that measuring a single qubit lowers the entropy by a constant amount. It turns out that this is not the case. This is not the case, in particular in this volume law phase. So measuring a single qubit doesn't actually lower the entropy by a constant amount. You somehow this intuition that if I have some entropy density, it's just sort of locally spread out among the qubits, and I can decrease it by a constant amount by making local measurement is not the right intuition. And rather, what happens in this volume law phase, in this system, is that there's somehow an emergent quantum error correcting code where these kinds of local measurements do not reduce this entropy, and I'll make this more precise as I go on. But somehow there's an intuition which is that, you know, these unitaries that you're applying when the rate of applying unitaries is large, somehow scramble this quantum information in the initial quantum state in such a way that it can't be destroyed by doing these local measurements. That's somehow the intuition. Okay.
Lukasz, I have a question, as a more basic question.
Yeah.
When you have this model where you have random unitaries and then you have measurements, you could also model the measurements by random unitaries that disentangle your states, right? Because eventually after the measurement, you just get a normalized state. So you can define the measurement using a random unitary, right? That would disentangle the state. So is your statement, when you compare the two effects of what you call random unitary and measurements, is really comparing two different kinds of unitaries, like an entangler and a disentangler? Is that?
Well, let's see. So I'm trying to see how to model a measurement as a random unitary. I mean, you can certainly model a measurement as, you know, as a unitary if you sort of bring in an auxiliary sort of ancilla qubit or ancilla Hilbert space, and so.
Well, let's say you had a singlet and you want to...
But Asa, I think that the issue is that if you want to disentangle a qubit, you would have to do a very non-local unitary. And the unitaries he's considering are local. I mean, if you have the... Yeah, so...
I see. So this is the effects of local versus non-local unitaries. That,
maybe, I mean...
Well, I mean, so very soon I'm actually start doing stuff that's non-local, but I think it's, you know, it's important to, I mean, so you know, in general, I mean, just a projective measurement can be modeled as a unitary, but you need an auxiliary Hilbert space. You need sort of, I forget exactly, you know, what the sort of the correct quantum information terminology for this is, but
yeah,
you know,
but if you have an additional ancillary, then you are not keeping individually every quantum trajectory. You're again going back to the picture of the mixed state.
Exactly. So if you trace out this ancilla, you're going again back to this picture of the mixed state. So that's somehow not what I want to do.
Right. No, I understand. You want to follow one trajectory, which has some random elements in it.
Yes.
And what I'm saying is that both the measurement and the random unitaries you said have different roles, but they're both random unitary operations, right? That, but I guess the measurement is highly non-local, perhaps.
But also the measurement, it's not really random.
Measurement outcome, you know, the probability. I mean, the other thing is that the probability of the different measurement outcomes depends on, you know, the norm of the projected state. And that's different from, you know, the sort of random unitaries that I apply, which just have, you know, just some fixed a priori probability distribution.
Yes. That's what I mean by disentangler. It's something that knows about the wave function.
Right, as you know, it's a very special unitary if you need to disentangle.
Yeah, exactly. Okay. So yeah, so you know, let me do one more thing of review. What time is it?
Yeah. Don't worry. We're not very punctual in Israel.
Well, that's okay. This talk is built so that it can end in various places. But so let me just mention this idea of a purification transition. It's actually a very related thing. It's not exactly the same thing, and there's, you know, systems in which the purification transition is actually distinct from the entanglement transition, but it's a very related thing. So you can actually do everything with the exact same setup that I already described. This figure I stole from the paper by David Hughes and Michael Gulans. So it's a slightly different setup. They do actual single site measurements like this, but it doesn't really matter. The details don't matter. The main difference in a purification transition is with the same setup, same Hilbert space, you don't start with an initial pure state, but rather you start with an initial mixed state. And specifically, you start with a maximally mixed state. And then what you see is whether that maximally mixed state gets purified or not as time goes forward. And the best way to think about this actually is, because mixed states are kind of hard to think about, the best way to think about this is think about your maximally mixed initial state as being purified by some ancillary system. So there's some ancillary system which you might call the reference, which consists, it's a Hilbert space of the same dimension. You might think about, same number of qubits, and you start with a state which is entangled between that reference system and the original system, say maximally entangled. Okay, and then you just see how that entanglement evolves over time. Okay, so again, if you just have purely unitary evolution, nothing will happen to that entanglement. So the maximally mixed state will stay maximally mixed. If you have all measurements, the measurements will rapidly destroy, the measurements are only happening in your original system. They're not happening in the reference. So the measurements will rapidly destroy that entanglement and you'll get a pure state. So there's a competition, again, this competition between measurements and unitaries, and it tunes the transition between a pure phase at large measurement rate, where the entanglement goes to 0, and a mixed phase where it doesn't. Okay. So this is the only reason I'm reviewing this is because it's a very related thing, but this is the context in which I want to talk about our results. Okay, so great. So like I said, okay, so that's the end of the review, and now I'm going to sort of mention the results that we have. So we wanted to study sort of what happens deep inside this mixed phase with very rare measurements. So a caricature of what happens deep inside this mixed phase is, so basically I want to motivate the model that we studied. So I'm not really claiming that this model, is a 100% faithful representation of what happens inside this mixed phase of the local model, but I'm just trying to rationalize why we wanted to study this model in the first place. So, if you think about sort of very rare projective measurements, what you have really is, you have some kind of a occasionally occurring projective measurement, which is just a rank n/2 projective measurement, where capital N now is the size of the Hilbert space, so capital N is 2 to the n. And then you wait for a long time applying sort of random unitaries. So you can kind of model this intermediate time behavior as just applying an essentially random unitary. You could just kind of imagine that, this product of local unitaries that occurs here somehow models an essentially completely random unitary inside the many-body Hilbert space. So what you really have is sort of a rank n/2 projective measurement followed by a random unitary. Rank n/2 projective measurement followed by a random unitary. And that's the model we decided to investigate. Okay, so this is a very simple model if you think about it. So all the spatial structure has been sort of thrown away here. It's really a model of just alternating completely hard random unitaries in some large capital N dimensional Hilbert space with applying a fixed rank projector, or really projective measurement, I should say. Okay, and just alternating this. So this is the model which we studied, and this model, it seems like, so we couldn't find any references on this, so it doesn't seem like there's any good results on this model.
The projector could also be on an entangled state, right? The projector somehow, it doesn't, it's not projecting on some sort of product state, yeah, the
projector is just a sigma z acting on a.
It is a sigma. You do think about it as like a projector on a single qubit.
Well, so yeah. Right now, I don't want to think about local qubits, so it's
just some projector in Hilbert space.
Yeah, it doesn't really matter, right? I mean, because you have a random unitary. So
yeah. Exactly, because you have a random unitary, the way you can think about this is actually 2 different ways. So you can fix the projector. and apply random unitaries in between, so like fixed projector and random unitaries in between, or you can sort of conjugate all the projectors by unitaries and just think about this as applying random projectors. So forget about the unitaries. You're not doing any unitaries. You're just applying completely random projectors in Hilbert space and seeing how a maximally mixed state evolves under that kind of time evolution.
Okay.
So this, as far as we could tell, was an open problem. Because I'm sort of won't have time to let me just preempt the results. So basically, we did a bunch of numerics and a large N calculation where we showed that what happens is that this does indeed purify, but in time that's time O of capital N, which is exponential in the sort of original number of qubits, little n. This thing does purify. And so let me show you some results here. So first, let me mention what it is we actually looked at. So, what you want to track is whether the state purifies or not. So the easiest thing to track, sort of from a computational perspective, is this purity, which is just trace of rho squared, right? So if you have a pure state, trace of rho squared is 1. But if you have a maximally mixed state, then trace of rho squared is 1 over n. So this purity starts off in a maximum mixed state as being 1 over n, and then you just want to track it and see how it ultimately reaches 1. Okay, so here I mentioned sort of some analytical methods, but let me skip that. Okay, let me say one thing, which is if you analytically want to compute this purity, you can kind of imagine that this is going to be a hard problem because this density matrix rho evolves under these random unitaries and these projections. So you can imagine you're going to have to do some averages over the unitary group, and there is actually a method for performing such averages over the unitary group, but the issue is that sort of no matter what you do, you're going to have to normalize a state, right? Because you have projective measurements. When you hit your state rho with a projector, it might not be normalized anymore, so you have to normalize your state. So you have to compute averages ultimately of quantities which are ratios like this, and this is very hard to do in any kind of analytical way. There's some replica method for doing this, actually computing the log of this, but we couldn't get any exact results to work. So first thing we did is numerics. So here's some numerics. I showed two curves here. So this is tracking the purity as a function of time. So the x-axis is time in number of steps of this thing, and the y-axis is purity. So the purity starts at 1 over n, and we actually show two curves. One is for the case of post-selection. So we do actually model post-selection just because it's easy, but the physically interesting case is the case of measurement. Okay, and so this is, I guess, a Hilbert space of size 2000, starting with a maximally mixed state and just hitting it with the random projectors and seeing how the purity evolves. And so, there's a couple features that we can observe here. So at initial times, there's sort of a linear rise in the purity, and it actually goes up in steps of 1 over n. At late times, the purity for this measurement case goes to 1. It turns out so does the case for post-selection, although much slower. So we didn't sort of graph it all the way, but that turns out to also approach 1. And this is a plot for a single quantum trajectory. Sorry, is there a question?
What is it? What is the post-selected curve? I mean, what's the difference between the two dynamics?
So the difference between the two dynamics is, in the case of post-selection, you really just hit it with a projector, a fixed projector. In the case of measurement, you apply either P or 1 minus P, depending on the measurement outcome.
Okay.
Yeah.
Do you normalize after you hit it with the projector? I mean, it's
yes.
trace 1, okay. And so how come it decreases the, how come it?
Yeah, I know, right? It's cool. Well, so here's the thing. I actually have a slide about this. So the decrease in the purity might seem counterintuitive because there's rigorous results you can prove that say that measurements. Let's just focus on measurements. Measurements should increase entropy, or in other words, let's see. Sorry. measurements should decrease entropy. So entropy can't increase after a measurement, or purity, in other words, cannot decrease. So purity should increase. But the point is that all these results are averaging over measurement outcomes. So in an individual quantum trajectory, they don't have to be the case. And in fact, you can cook up sort of simple examples of a density matrix where where a measurement can actually decrease the purity because well, okay.
Okay. Oh.
Yeah. Okay. So let me just mention some features of this model. So,
but just one thing. But once you hit a pure state, then you will never leave it. I mean, you will stay there.
Exactly. So once you hit a pure state, you will never leave it. So in the case of post-selection here, this didn't quite get to a pure state. I mean, it looks like it on the curve, but yeah. But once you actually honestly hit the pure state, then okay. You will never leave. Yeah. So there's some features to explain. So there's then sort of an initial noiseless growth of purity. The late time behavior also looks noiseless, and then the intermediate dynamics looks noisy. We weren't able to explain this analytically. We don't have a full analytical treatment. What we do have is just some large N calculations. I don't really have that much time to describe these, but let me just sort of give the general flavor. The idea is there's a large N limit that you can do here. So in the large N limit, things simplify. And in particular, in the large N limit, you can sort of compute things almost exactly for a single time step. Okay, so if you apply again, I'm applying random measurements. If you apply a random measurement to initial state rho 0, you can see how how the expected value of the purity evolves for the normalized state. Okay, so this is sort of averaging over the randomness in the choice of P and the randomness in the measurement outcomes. And so if you sort of do this large N computation, you can see that there's a 1 over N term and another term which you could actually rigorously bound as being 1 over N to some power greater than 1. So you can ignore it relative to the first term in the large N limit. It's not an uncontrolled expansion. I mean, the error term is rigorously bounded here. So this is for a single step. You can see that if you start with something that has very that's very mixed, rho 0, your rho 0 is very mixed, then you can ignore these two terms and you really just get this 1 over N. So this sort of explains that when you start off with your initial mixed state, there's this sort of 1 over N increase to begin with. You could also apply this analysis to late time behavior, where your purity is close to 1, and what you can see is that if it's close to 1, it's going to get even with each time step. So this is
just a single time step. I mean, what you're showing here.
This is a single time step. This is one single time step, one single random measurement. Yeah.
And N is kind of the number of qubits, quote unquote. It's just the dimension.
N is 2 to the number of qubits.
Yeah. N is 2 to the number of qubits. I see. 2
to the number of qubits. Yes. So this thing converges roughly in time capital N, which is 2 to the number of qubits. So it's a very long time.
I see.
Yeah. Okay. So this is just some large N stuff. You can also compute the noise. That's a little bit more of a complicated calculation, but it basically shows you that the noise at early times is going to be very small, and at late times is going to be very small, and at intermediate times you have no reason to expect the noise to be small, and so that's why you see, well, that's consistent with seeing these large fluctuations. Okay, so you can also do post-selection. Let me not talk about that, but that's basically the upshot. So what I want to say is that we found it sort of surprising that this model hadn't been solved exactly. Maybe there's an exact replica solution for this model. I don't know. There's sort of a lot of open things that one can do here. Now, in my remaining 5 minutes, let me discuss free fermions. So here I'm not going to be able to explain much, but I'll at least be able to state the result. So this is switching gears a little bit. So we're not thinking about this sort of non-local model anymore, but rather we're now looking at not a Hilbert space of spins, but a Hilbert space of fermions. Okay, so again, you can imagine a chain of fermionic sites, and each site has, two possible states: fermion occupied or fermion empty. But now this is a fermionic Fock space, and you can look at a restricted class of unitaries and a restricted class of measurements, which are basically free fermions. Okay, so you can look at unitaries which are free fermion unitaries, by which I mean they're exponentials of I times the Hermitian operators, which are such that the Hermitian operators are quadratic operators and the creation annihilation operators is what's meant by free fermions. And you can look at measurements which measure basically occupation numbers of various Fock space modes. Okay, so I sort of already mentioned why one would want to look at free fermions. One wants to see if you can study these transitions with free fermions. And there's two possibilities. You can look at particle number conserving dynamics, or dynamics where particle number is only conserved modulo 2. So let me just discuss the particle number conserving dynamics case. So here, the nice thing about free fermions is you don't actually, you don't have to keep track of the state in the whole many-body Hilbert space. Rather, because it's a free fermion state, it's actually uniquely determined by the so-called correlation matrix, right? So this is I should have mentioned this earlier. So with these free fermion unitaries and free fermion measurements, the entire evolution takes place among these so-called class of Gaussian states. So Gaussian states are basically a very restricted class of states in Hilbert space. You can think of them as sort of Gibbs states for free fermion Hamiltonians. But it turns out that free fermion evolution makes you stay within this class of Gaussian states. So if you start with a maximally mixed state, which is a Gaussian state, and you apply these free fermion unitaries and free fermion measurements, you stay within the class of so-called Gaussian states. And Gaussian states have the property that they're completely determined by this correlation matrix. So if you sort of know the 2-point correlations, you know everything. So you can sort of model the evolution here by just seeing what happens to this correlation matrix. So under unitary evolution, sort of the obvious thing happens: the matrix just gets conjugated by the corresponding unitary operator. Under measurement, it turns out that you can also keep track of what happens. It's fairly straightforward. You can keep track of what happens to the correlation matrix under a measurement. So I wrote it out here. I don't have time to really explain it. But let me just get to the punchline. So the punchline is, you want to study whether, we want to study the late time purification behavior for these Gaussian states in the context of this free fermion dynamics. It turns out that it's actually kind of annoying, kind of difficult to write out the formula for the actual, Renyi entropy or purity or whatever of the many-body quantum state in terms of this correlation matrix M, but it's easy to write down a definition of another quantity, which I called here the proxy entropy, which has a very simple formula in terms of this correlation matrix capital M. So this proxy entropy is only defined for the class of Gaussian states. It doesn't even make sense for the full, it's defined in terms of this correlation matrix M. I guess you could in principle define it for general many-body states. But what this proxy entropy, the property that it has is that, it's not equal to the second Renyi entropy, but for the class of Gaussian states, it's stays within positive uniform order 1 constants of the true second Renyi entropy. So if all you care about is sort of purification behavior, whether the state ultimately becomes pure or whether it stays mixed, you can just track this proxy entropy, which is much easier to compute. And that tells you about what the true second Renyi entropy is doing for this class of Gaussian states. Okay,
what is little n here?
Little n is the number of Fock space modes.
Okay. Mm-hmm.
Yeah. So the Hilbert space again has the dimension of 2 to the little n. So yeah. So since I'm running, let me just get to the punchline here. So we study this proxy entropy, and what we showed here is that a measurement for any Gaussian state, as long as you sort of measure all possible modes equally likely, doing a measurement, just a measurement of a Fock space occupation mode averaged over the different modes in the system actually does decrease this proxy entropy by at least little s squared, where little s is the density of this proxy entropy. So in other words, I sort of made a big point of saying that in the original context with sort of general unitaries, you can hide quantum information in such a way that it cannot be, you cannot decrease entropy by an appreciable amount, but by making measurement. But here the point is that with free fermions, you cannot do that, which is maybe not surprising. You can't make a quantum error correcting code with free fermions. But basically the upshot is that measuring a single fermionic mode will decrease the entropy by some amount. It doesn't decrease it by as much as you might sort of naively hope if the entropy was locally locally distributed in the system. So measuring, it's not like by measuring a single fermionic Fock space modes, you distill an amount of entropy which is proportional to the entropy density. It's actually the entropy density squared, which is a smaller number at low densities. But it turns out that this implies that the system does indeed purify in polynomial time. So you can show that it purifies in time little n squared, where little n is the number of Fock space modes. So anyway, so this is related to sort of there's a bunch of related works which sort of found that they were unable to realize a volume law entanglement phase or a mixed phase for this purification system with free fermions. So this is kind of a nice explanation of that. No matter what the context is, you cannot quite realize a mixed phase with free fermions. We had I'm not going to discuss this, but you can do a version of this with fermion, with systems which only conserve fermion parity. It's a little more subtle in that case, but there's some caveats which I'm not going to really mention, but a similar analysis goes through. Okay, so so this is where I want to end. I'm already at an hour. Like I said, we don't have a lot of sort of rigorous results. We didn't actually quite analytically completely solve our sort of original model. So I think there's sort of a lot left to do here. Like it would be nice to possibly completely solve this model that we, with these random projectors acting in this many body Hilbert space, possibly using some kind of a replica analysis. We couldn't quite get that to work, but maybe it's possible. And obviously exploring the actual phase transitions would be interesting too. So everything that I talked about was sort of happening not at a phase transition, but sort of in one phase or another. So it would be certainly interesting to look at phase transitions. Okay, so let me end here since I'm already over time and take any questions.
Okay, thank you very much. So questions? So I could start. I have a couple. Say ask one. So you kind of solve the model where you really somehow assume that the measurements are so scarce that you can really think about a random UN, but so that's the limit where the rate goes to zero. For any finite rate, you're right. Becomes important, right?
The what becomes important?
Somehow there's a finite time between measurements, and then the local structure becomes important.
Exactly. Yeah. So you're right. So the model that we solved doesn't quite there's a order of limits issue which is important, which is the order of taking the thermodynamic limit of infinite system size and taking the measurement rate to zero. Right. So we kind of sort of did the limit where we first we fixed a large but finite system size, and then we took the measurement rate to zero first. But you're absolutely right, that doesn't necessarily commute.
But do you think, do you believe that if you would reverse the order, so if you, then you would again see that the mixed phase has a exponential.
I think so. I think so. And I know Matthew Fisher and his students did a completely different analysis in a local model, which seems to indicate that you still have an exponential purifying behavior. Somehow the locality only helps you purify, right? Because the locality just makes it so that you're not scrambling as much as you possibly could. We're kind of giving the unitaries the biggest possible chance to scramble the system by taking completely non-local unitaries, and it still purifies.
So is it really a phase, or it's just kind of a glass? Is it, think about more like a glass?
Yeah, I don't know what the right terminology is, but it's I mean, yeah. Yeah, I don't know what the right terminology. I mean, there is a sharp behavior. It's a sharp the transition. There's a sharp change from exponentially long to polynomially long. But would you really call that a phase? I don't know. Yeah, good question.
Okay. Questions? Other questions?
What is it's a more general question. So what is the general motivation for understanding these type of models? I mean, what are we trying to model here? I mean, it's not like I mean, it's discrete dynamics. It's something that is very natural for, I guess, in some sense, quantum computers maybe.
Yeah, that's right. So if you look at these papers, there's usually a paragraph about closed quantum systems and quantum computers, and I mean, like this purification picture, for instance, where your mixed state is thought of as a pure state, which is it's purified by some reference. You can think about that maybe as some quantum memory where you have some entanglement, and then you have some sort of local measurements which are trying to destroy that entanglement, and so it's kind of nice that that entanglement stays preserved. If your measurement rate is below a certain threshold, assuming that you also have these unitaries. I mean, that's people's motivation. Honestly, as for myself, it's just it's a new kind of dynamical phase transition. So it's always just interesting to sort of study new phase transitions. Yeah, I don't know. I think that's the best motivation that I can give. It's just something new.
Right. So and maybe it would imply some hardness of computation or easiness of computation for the type of system.
Hardness of computation.
I mean, if you have an area law, and maybe it's easier to simulate these systems using, I don't know, MPO.
Yeah. Certainly. That's right. Yeah, I don't know if that's been leveraged. I mean, seems like if you're gonna, that's a good point. I'm not sure if that's been used. But certainly, a system in the pure phase, in the purifying phase, should be easier to simulate, I think. So in the area law phase, certainly it should be easier to simulate.
I have a question about the entropy. If you look at the maximally entangled state, that's, I guess, a state that you would say obeys the ETH conjecture, right? It has it's like a many-body eigenstate that has a local entropy that's Boltzmann-like, right?
Yeah, I mean, it's you can think of it as a Gibbs state for the zero Hamiltonian, I guess.
Right. Okay. So you start with a state that has that property, and you let it evolve. What I'm interested in is what would happen to the real density matrix, averaged over all the measurement results. Would it change, or would it do something?
So
what is the dynamics?
The density matrix. Well, yeah. So I mean, if you start with a completely mixed state, so let's think about this. Well, so I mean, so there's two contexts that we can talk about this. So we can talk about this in the context of the original entanglement transition, where you start with a pure state, and you can ask, okay, so that pure state will evolve into an ensemble of pure states, and you can construct the density matrix there, and you can see how that evolves. So that's going to start with some very pure density matrix, rank one density matrix, and it's eventually going to, it's going to evolve into some mixed density matrix.
Yeah, right. And now you want to put in these measurements. What I'm interested in, how is the dynamics going to look like now for that density matrix?
Yeah, so I mean,
if you take the ensemble, then at some point, if you make enough measurements, the ensemble would just be mixed, totally mixed. I mean.
Yeah, right. Yeah, that's right. So my guess is that no matter what, like you would just get some kind of a very mixed density matrix, and regardless of whether you're in the, let's see.
If you co-select, then it's a different case. But if you,
would you see any signatures of these time scales that you found in the when you're looking at single state?
I don't. Yeah, so I mean, short answer is I haven't thought enough about looking at the density matrix, but somehow I don't think so. I feel like none of this is visible if you just track the reduced density matrix. Why is that? I mean, can we imagine like some limit deep inside the area law phase where you mostly do measurements but only occasionally do a unitary? Is that enough to make the?
Well, it looks to me like, again, translated to like condensed matter. You have a random noise, that's your random unitaries, and then you have these dissipative processes of measurement. Yeah. And the question is, what does it affect the density matrix? And usually the effect is not large, but you could see differences between a density matrix that has a lot of quantum correlations and one which is described by classical, evolution or.
Right. I mean, the other complication is that, yeah, there's choices of randomness in the choice of unitary. So even if I forget about the measurements, applying random unitaries, that's already gives me an ensemble of states. So I already get some pure state evolving to a mixed state there. So somehow I have to be able to separate that complication from just the inherent randomness due to measurement outcomes. Short answer is I can't give you a good answer right now. Yeah.
Okay. No, I just thought it's an interesting.
Yeah, it's definitely worth thinking about.
What?
Yeah.
Lukasz, in this fermion model, what happens if I add a say small amount of interactions? I mean, would I lose this polynomial in a sharp way? What do you think would happen?
Oh, that's a good question. That's a good question. Yeah, if you had a small amount of interactions.
Yeah, is it like some sort of instability that I lose?
Yeah. No, that's a really good question that I don't have an answer to. Again, this work is very sort of, we don't have a lot of rigorous results. We just put some stuff out there, and there's a lot of good questions that one should think about. I don't even have an intuition one way or another. Because you can imagine sort of approximately free fermion with some small interactions.
Right. Yeah.
Is that enough to mess it up?
Yeah.
Yeah. Excellent question. Worth further study.
Mm-hmm. Okay. Other questions?
Can I ask a question?
Go ahead.
Sorry. Okay, go ahead.
I'm just wondering in that where you see the purity getting bigger and bigger in that intermediate region.
Yes.
Can you say that it's just like there's one number that's sort of like the temperature, and otherwise it's a completely random matrix, or can you see there's some sort of other correlations or some property that it remembers how it got there?
In which regime?
Like in the intermediate, when it's like fluctuating up and down. Think of it just like a random walk, where the size of the steps depends on, it's just fixed by the amount of purity at that time.
Right. So so there's this thing that I didn't talk about, which is this graph here. So you can do a simpler case of rank 2 density matrices. And so if you start with, instead of maximum mixed state, just a rank 2 density matrix, for a rank 2 density matrix, the purity determines the spectrum. So the purity really does determine the state completely. So it's just, in this case, it is a completely, it's a Markovian process. Like once you know the purity, you know your state.
Mm-hmm.
I don't know if this is what you're getting at or not, but
yeah, but I guess in a larger matrix, there might still be something like that, just sort of like in thermodynamics. If you know the temperature, you know the ensemble.
Yeah, that's right. Yeah, that's a good point. But it's certainly true in this rank 2 case, and in the rank 2 case, you certainly also see these sort of long decreases. But in the higher rank case, it's plausible that something like that's true.
To test it, like with some kind of correlation that every time it reaches a certain purity, does it have the same distribution of?
Oh, I see.
Something without being able to derive it, maybe you can test it and then.
Yeah, that's an excellent point. Yeah, we should try to do that.
I mean, are these figures? Do you average over trajectories here, or
no? This is just a single random trajectory.
No.
Yeah. So if you averaged over all possible trajectories, this wouldn't be able to decrease.
Yossi, you wanted to ask a question?
No, I'm happy. Thank you.
So there's some other question that we not address. All right. Okay. So yes, very interesting.
Thanks.
Okay, man. Thanks a lot. I think we can go back to drinking coffee and I don't know, go running or whatever.
Thank you.
Okay, one of these days we're gonna get to go skiing.
Yeah. Next year, I guess.
We'll see. Oh, there's no new variants.
We almost got it last year.
I know. We were like, they literally canceled it the day before. I was so pissed. I was like, oh. Oh well.
Yeah.
All right.
Yeah.
See you.
Have fun.
Harry.
Say hi to Sarah. We'll be in touch.
We'll do.
Huh?
Bye.
Good thing.
Bye. Bye.